Hi everyone, I'm Harry Liu from Microsoft Research, and today I will tell you a beautiful story of the marriage between theory and software-defined network. And today I will talk about how can we achieve efficient and robust traffic engineering with a concept called forward fault correction. So nowadays, cloud services are rapidly growing, which gives the cloud network a very huge pressure. So on one hand, the traffic demands are ramping up very fast. On the other hand, it's really expensive to build and maintain new networks. So to handle this tension, and it's more and more important to consider, to emphasize the efficiency of the network. And this is why people are motivated to study how to use traffic engineering, which is centralized and SDN-based, to boost the network efficiency. And they already show that they are effective and have huge potential. And let's use a simple example to show you what is traffic engineering and why centralized TE is the key to network efficiency. So this is a very simple network with 4 nodes, 4 links, with link capacity with bandwidth 10. And one flow reach this network. And for example, if the source is 1, node 1 needs to make 2 basic traffic engineering decisions. First, how much traffic to admit to the network, and second, how to route to the destination. And in this case, let's assume it admits the fully 10 bandwidth and use 2 paths to forward the flow, and each path had 5. And later, there's another flow comes from 2 to 4, and then 2 makes the same decision, but at this time, 2 only see 5 capacity from 2 to 4, so it only admits 5. So in total, the throughput is 15. And obviously, this is suboptimal because optimal throughput should be 20. And the suboptimal is caused by the local decision between 1 and 2. And if we have a centralized TE controller and it knows what's going on globally in the network, and to configure multiple devices to make it can achieve the optimal throughput. So overall, the centralized TE's architecture is like this. So we have a conceptually centralized controller, and it keep monitoring and controlling the network. It has a network view, including the topology, capacity, and traffic. And it makes the TE decision and translate the TE decision to network configurations and push all the network devices. And because the traffic is changing all the time, it also needs to frequently update the network configuration to achieve the high utilization. And this architecture also have a weakness. It's because the TE controller is monitoring and controlling the network remotely, so it's very vulnerable to the faults that can happen in the network. And today we will focus on 2 kinds of faults: data plane faults and control plane faults. So data plane faults means the device and the link failure. So when this happens, basically the topology has been changed and the capacity has been changed, and it will cause severe congestion. For example, given this network, suppose there are 2 flows going through. Each flow are using 2 paths from the source to the destination. And if the link from S2 to S4 goes down, what happens next is that the S2 will very quickly do a local reaction. The local reaction is called rescaling, which means it will stop sending any traffic on this field path. Instead, it will proportionally send all the traffic to the residual path. So in this case, there's only 1 residual path. So after the rescaling, the traffic distribution will be like this, and there will be a link congestion. And the other kind of fault is control plane faults. That means the failures or long delays to configure a network device. So it's caused sometimes by the TE controller's communication, and the communication channel can break. And also in the switcher side, there are a bunch of problems that prevented the switcher from responding to the configuration. So you can see if you want to reconfigure a bunch of switches and some are not responding you and still use the old one, this mismatching will also cause severe congestion. So for more example, you can refer our paper. And let's get back. So now let's understand why exactly the data plane faults and control plane faults are are causing problem because basically the data plane faults make the topology and the capacity of the network keep changing, and it creates inaccuracy in the network view to the network controller. And on the other hand, the control plane faults create incompleteness of the network configuration. And this seems to be a very fundamental problem when we use this centralized control architecture. And now the problem is whether these faults are very common. And unfortunately, yes. So we did a study on Microsoft One, and which is a larger scale network. We found that these two kinds of faults are very common, and from time to time, they are causing severe problems. For example, we found that every 5 minutes, you have a 1/4 chance to have at least one link goes down. And each time you want to configure a switch, there is a 0.1 and 1% chance that you cannot configure it. And in the fully utilized network, even a single failure will cause severe congestion. This shows the link oversubscription when we introduce a single link failure. So because this is so common and so important, we want to see how to handle it. And let's first look at what's the state of art. So currently, there are only two methodology mainly. The first one is heavy oversubscription, which means blindly leave spare capacity everywhere in every link. Hopefully, that can work. But actually, this usually does not work. But the one thing is for sure that we will have a big loss in the network throughput. And the other methodology is to react to faults. We don't do anything until the faults happen. But remember that in the real network, a large scale network, reaction is really slow. And when you react slow, it means that you cannot prevent any congestion from happening. And a reaction means another round of network configuration. And this round of configuration can still blocked by the control plane faults. So the network will be messed up. And instead, what we want to do is to consider a new angle. So how about handling the faults proactively? And it means that if the network we cannot assume is 100% robust, can we build any robustness into the TE algorithm so that when the TE algorithm figure out a network configuration and when it configures the network, the configuration does not only valid in the current situation of the network, but also can handle the dynamics and uncertainties that can happen in the near future of the network. So when some problem happens, the configuration can fix itself, and without the reaction of the TE controller until next 5 minutes, it just configure a new configuration. So if we go along this way, we are facing a challenge that no one is knowing what exactly will happen in next 5 minutes. So because the individual faults are really unpredictable. But we also have some good news because in next 5 minutes, the simultaneous number of faults should be small. And this reminds us a very similar case in the communication. When the sender sends some receivers some packets over a lossy channel, and it's almost for sure that some packet will get lost, but you never know beforehand which packet will get lost. So people created the concept called forward error correction. That means I want to encoding the data in the case that if only the number of lost packets is up to k, I can recover all the information. So given the similar situation, we create a similar concept, which is called forward fault correction. That means we want to find a network configuration, a traffic engineering, that can guarantee no congestion if only the number of faults is under k. So we all know that FEC retrieved this concept with a carefully designed data encoding, and we achieve this concept with the carefully designed traffic distribution. So before showing you how we systematically achieve FFC concept, let's look at the example to show you this kind of robust TE does exist. So this network has 2 flows, and the traffic demand is 9, and they are using 2 paths, and split with 1 and 8. And I would say this is FFC k equals to 1 for the link, so it's resilient to any single link failure on this topology. For example, when this link goes down, and after the rescaling, the traffic is like this. And when this link goes down, no congestion. And because the traffic and the topology are symmetric, so you can verify the last 2. So there's no congestion under a single link failure. And what's more interesting is to put non-FFC and FFC traffic engineering together. And the first one is non-FFC. The third one is also non-FFC. But if we compare the first one and the second one, we can see the trade-off between throughput and the robustness. And if the throughput requirement is 30, we have no way to find any FFC traffic engineering, because for the robustness, we have to leave some spare capacity on some critical links, and it will have some overhead on the throughput. But what's more interesting is to look at the second one and the third one, and know that they have the same throughput. The only difference is how you spread out the traffic distribution. And it means that FFC sometimes is free. It's just a matter of whether you're smart enough to find a good traffic distribution. And based on the trade-off between efficiency and the robustness, we want to find a sweet spot in this trade-off. What we want to find is under a kind of FFC guarantee, we want to find the traffic engineering that achieves the optimal throughput. By optimal, I mean that I can fully satisfy all the traffic demands, or I can satisfy them as much as possible. So now let's systematically consider how to achieve FFC. And we have two questions to answer. First, how to model this concept. Second, how to find FFC TE. And currently, people typically use linear programming to find the traffic engineering solution. And basically, they make the T decision as variables, and they have some objective to achieve. For example, maximizing the network throughput, and they have some basic TE constraints. And if you translate English into the linear programming, it will be straightforward. And because FFC is the further requirement to the final traffic engineering we want to find, so it's naturally to think whether we can just plug in some FFC constraint that can guarantee that the final traffic engineering decision we find achieve the FFC requirement. We call this FFC constraint. And now the question is, what does it look like? So first, we use a simple example to show you what does it look like. And suppose there is one flow, and the source is S, destination is D. And from source to destination, there are 3 paths. And we assume that the paths are link disjoint. So a single link failure can at most turn down one path. And what we need to decide is the flow size F and the bandwidth allocation on the 3 paths. So if we have the FFC k equals to k, that we want it to resilient to any single link failure, what it means that when link path 1 goes down, path 2 and path 3 has sufficient capacity to deliver the flow. And similarly, when path 2 or path 3 goes down, so the other 2 will have sufficient capacity to deliver it. So overall, it's a 3 choose 2. And you can easily see that this is the necessary condition for the FFC. But in the paper, we have lemma that if finally you set the path weight like this, and it will become a sufficient condition. So when it's achieved, it's guaranteed that FFC is achieved. So let's generalize it. If we generalize it, and if for this flow, if we have n paths, and we want to decide the bandwidth allocation along this n paths, and we want to be resilient to k-link failure, that means the arbitrary n minus k, that is residual tunnel, should be enough to support the flow size. And if we write this requirement down, we will have n choose k constraints. And we call this a group of constraints is k-sum constraint, just for naming. And then let's go back to look at the architecture, the structure of the FFC TE formulation. So we have normally objective basic constraints, but we have a lot of FFC constraints. And the FFC constraints consider many group of k-sums. And this is just for data plane faults. For control plane faults, you can also formulate it finally the k-sum problem. So now the challenge is we have, in the larger scale network, we have two too many constraints. We cannot solve them directly. And what we want to do is to achieve a lossless compression of this K-sum constraint format, which means we want to find a small number of constraints that can sufficiently represent the original constraint and still achieve the optimal objective. So there's no loss in the optimity of the objective. So in our original paper, we found a way based on bubble sorting network. We reduced it from n choose k to kn. And recently, we have progress. So we found a way to reduce it to on. And because this is a short talk, I won't show the details, but you can visit my homepage for the details. And in the project, we also find that in traffic engineering domain, there are many extensions that we found FFC is just like a plugin. It can easily plug in the existing system and just add some more constraints and solve it and find a more robust Te. And it can extend to support different traffic priorities. And even if there's no traffic limiters, and we can still use FFC to minimize the congestion. So now I give a highlight of the implementation of the evaluation. So I only have 2 points to stand. The first one is FFC can fully implement it in the community hardwares. And the second point is that with the real network topology, real traffic, real event, we find that actually FFC's throughput loss is negligible, and but it can reduce the data loss significantly. So here is the conclusion. You can find that we go back to this figure, but we change this to SDN controller. I believe a lot of SDN system will have the architecture like this, and it will suffer from the same problem that the TE controller suffer from. Basically, with SDN, with centralized control, we want to achieve a lot of and keep a lot of network properties, but a lot of network faults that will prevent us from achieving that. And in FFC, it is just to solve a sub-problem of this whole domain. And by presenting this, I hope I can route more discussion and research on this topic. Thank you.
We take questions mostly offline if you want to report on this.
So did I understand correctly that to use FC, you also need FEC to encode the data as well, because when you have a fault, we want the data itself to be full error.
I think that's independent. So by using FFC, you guarantee that there's no congestion. Yeah.
So at the end, you mentioned that you can do it with order n constraints, so it's independent of k.
Independent of k.
But this should not work for large k, right?
It should work. So we can discuss offline. Actually, I have a technical report. Yeah. Thank you.